Hi, my name is Leandro Costalonga. Before we start, I would like to apologize for not being able to attend the conference in person, but it was a last-minute thing regard to my wife's and baby's health, so I'm pretty sure we can all sympathize and understand that. I'm sure you all have noticed how technology can impact our lives. And the term cognitive offloading is regard to that. Is the use of physical action to alter the information processing requirements of a task so as to reduce the cognitive demand to perform that task. It could be something as simple as using your phone to remember an appointment, or maybe just tilting your head to look at a rotated image. We are interested in studying that because we belong to a network of research groups that study ubiquitous music, and among other things, ubiquitous music, or ubimus, is regard to design musical things accessible and available even for non-musicians. And from our side, we do that by creating games, toys, and mainly artistic multimedia installations, which we believe is a great way to understand the interaction between the general public and a musical activity. Another project that we have been working on is the RoboMus. It is basically a framework to build musical robots using spare parts and recycled parts by students from the computer science and computer engineering course. These robots can interact with each other and can also interact with a human musician, which we believe is a great umbrella project to understand more about how humans interact with robots in a transparent way. Another area linked to this idea is the Internet of Musical Things that explore new ways to engage into musical activities using these smart musical instruments. All in all, it is a matter of human-computer interaction, specifically interaction design. And our ultimate goal is actually to provide some guidelines to designers so they can create a more engaging digital musical instruments device. In order to us to create better technology, we first need to understand the users, and we can do that by studying the ergonomics and the human factors and see how the human body conform and fit to the task, and can also study that by using the cognitive aspects that is demanded to perform that tasks. This is not something new and has been known as conceptual frameworks for cognition. One of the most prominent models is known as MHP, it's the Human Professor Model, and it has been used to calculate how long a human takes to perform a certain task. It was created in 1983 by Card, Moran, and Alan Yu. Considering that the cognitive science is one of the roots of HCI, external cognition is not something new to the HCI community. An impressive range of tools has been developed throughout history to aid cognition, and could be simple technologies such as pens, calculators, or more robust ones such as computer-based technologies. The fact is that the combination of the external representation and the physical tools that has greatly improved and support the people's ability to carry out cognitive tasks, especially those that are more demanding. There are simple and common strategies involved in this external cognition process. One of them, and the most common one, is to reduce memory load by externalizing this knowledge using diaries, reminders, calendars, to-do lists, so on and so forth. Another approach is the computation offloading, that is basically use external representation and a tool or device to perform a computation. The most basic one would be pen and paper to solve a math problem. Cognitive tracing and annotating is also very common, and it implies that modifying representations to reflect change. Could be something like crossing off or underlying items. Along these lines, Barr and his research fellows have forged the term extended mind, and this has been used in order to refer to the notion that our cognition goes beyond our brains, usually suggesting that individuals may allow their smart device to do the thinking for them. This ability to rely on external mind can have some detrimental consequences to our cognition because it changes the way we do things. And this has been one of the most pertinent questions of the 21st century. So, how this increasingly intelligent and invasive technology will affect our minds, and how does this apply in a musical context? For example, when people expect to have future access to the information, they present a lower rate of recall this information. And, well, they know where to find it, so they don't need to memorize it. This, in turn, can have impact on our short-term memory. In a musical context, Gabrielson has shown us that short-term memory is fundamental to the segmentation strategy used when we are reading a musical score. It is in this first stage of reading the musical score that we develop the performance plan. It is where we have the first ideas about how to perform music and understand the structure of the music. So with the new generation making an excessive use of this intelligent and invasive technology that may impact short-term memory, how can we expect them to be good sight readers? This can even have an impact of how we persist and write music. So based on that, we decided to study more about the origins of the music, the underlying mechanisms that allow us to perceive and produce music. And this has been called musicality. It has been defined as a natural, spontaneously developing set of traits based and constrained by our cognitive and biological system. Music itself is just a product of musicality for this purpose. However, this notion of musicality has been a bit controversial. Most scholars were wary of the notion that music cognition could have a biological basis. They believe that we have not been around long enough to have shaped perceptual mechanisms specific for music. This is different when we think about speech and language. Nevertheless, more recent studies has indicated otherwise. What can be agreed on is that all humans share a predisposition for music. In the same way that we have for language, for example, recognize a melody or to perceive the beat of music. These are examples of traits based on and constrained by our cognitive abilities and the underlying biology. Even infants, they are sensitive to such features, and that is common across different cultures. Even people who consider themselves in music, they have an implicit knowledge of musical forms and styles of their particular culture. If you think about it, we can find music in all cultures and all time periods, and these say something. And it becomes even more interesting when we realize that some of the fundamental mechanisms that underlie human musicality are shared with other species. For example, the drumming behavior of our nearest relatives, the chimpanzees, or the commonalities of a bird and whale song. It is out of the scope of this presentation to go deeper into this particular matter, but recent advances in molecular technologies has been proving that. We are short on time here, so I won't point out every single cognitive trait that we have studied. You can find that on the paper, but we have mainly grouped them in 5 different categories. First one relates to materiality, and it is about how we relate to physical objects instead of the digital ones and virtual ones mainly. The second one is about rewarding state of consciousness called genotropic state, that is about the pleasure of engaging to a music activity. The third one's about gesture and movements, the natural mappings that we have and we use for music. The fourth is entrainment, synchronization, and beat perception, which is something that we share with different species. And the last one is imitative behavior, that is useful especially for musical learning. For each of these groups, you'll find on the paper some examples of how to make the most of the cognitive traits involved in this particular category. It's a kind of a guideline. For example, when we talk about imitative behavior, we see that true imitation is something innate. So it is something well developed in humans and being observed in newborns, both for fostering learning and for pleasure. We know that true imitation focuses on goal instead of the function, and therefore learning to play a musical instrument is basically a typical example of true imitation. There are other forms of imitation as well, and based on that, we can suggest some implementations such as the comparison mechanisms that allow casual players to match their performance against more skilled ones, or tutorials with professional players, or even the adoption of elementary motor gesture movements in an effort to reduce motor-related learning and making sure that these movements also does not conflict with one another, and is something feasible and comfortable for the user. Finally, would like to leave some food for thought here. We know that ergonomic and cognitive and biological traits that support all this musical activity, they from producing to enjoy music, has been largely the same throughout history. We know that new technology such as ubiquitous music, Internet of Musical Things, and new interface for musical expressions, they're all very exciting research lines, but there are some big questions about that. For instance, are we cognitively equipped to make the most of this new technology? Could we thrive in actually this way of making music, or will be just something short-lived, cool, but we won't put enough effort to master it? Also, is this new technology really paying attention? We as designers are really paying attention to the way humans do things musical-wise? Are we taking into consideration what we are good and what we are bad at? And finally, something that we are not able to answer as yet, is this technology actually shaping the way we make music, and it is shaping our underlying mechanisms that allow us to do music as we know? So if you have any comments or questions, please let me know. Mail me. I will try to get back to you as soon as possible. Once again, I'm sorry for not being able to attend the conference, and I hope to see you all very soon. Thanks.